So yes, good morning or good evening, depending on where you're watching this from. My name's Kevin May, and I'm speaking to you live from Galway City on the west coast of Ireland, where I have been a software engineer on the Arm NN team since 2018. So, quick introduction. Here's a quick rundown of what we'll be talking about. I'm sure there's many of you who are familiar already with Arm NN, maybe even you've made a pull request, but equally there may be some of you who have little knowledge of what Arm NN is. So I'm not going to make any assumptions, and we'll start with an introduction to Arm NN, what it is, why you would want to use Arm NN, and then a nice real world Arm NN use case. And then we'll get a look in detail at some of the new features introduced in the past few releases. So PyArmNN, which is our new Python API. We'll have a look at 2 new backend features for power users of ArmNN. And we'll have a look at some of the new data type support we've added, and a look at the in and driver operator support that we've added. And if we have time, then I'll give some information on how you can also contribute to Arm NN. So what is Arm NN? It's an inference engine for edge machine learning. So that's the first thing. It's for inference only. It doesn't concern itself with training. And it bridges the gap between existing popular neural network frameworks. So TF Lite, ONNX, PyTorch via ONNX, and Caffe. And it bridges the gap between those and underlying IP. So for example, Cortex-A CPUs, or CPUs, and the Mali GPUs, and also Arm's new Ethos-N NPUs. In addition, it provides NN API support, so Arm NN interfaces with Google's Android neural network API using the HAL driver to target Arm IP. And it's through the sufficient targeting of Arm IP using Arm Compute Library and the Ethos-N driver stack that Arm NN can deliver some real performance improvements, which we'll see. So here's a quick overview, which I think is useful to give us an idea of where it sits in relation to high-level neural network libraries and Android applications. So the blue components here are Arm NN, which consists of the HAL driver that provides access to Arm NN for Android applications. And then the Arm NN SDK itself, which provides the backends here for the lower level libraries and hardware drivers. So the backends that are by default added would be the Neon backend and the OpenCL backend. These interface with the Arm Compute Library, which provides access to the Cortex-A CPUs and the Mali GPUs. But we've also available to download in addition is an NPU backend. And that would be for the access to the Ethos-N processor. And of course, if you are a third-party partner, you can also add your own backend for Arm NN via our pluggable backend mechanism. So I've added this slide because this shows the inner components of Arm NN, and this will be useful when we talk about some of the new features, just to put them into context. So I'm using blue again to designate Arm NN components. We'll start here. These are the 3 main flows of when you'd be using Arm NN. If you look at the direct API here, this is how you would use Arm NN if you were to build up your neural network layer by layer yourself using our direct API. But probably more likely is how you would use our parsers in this black box here. So we'll say the TF Lite parser, the Caffe parser, or the ONNX parser, or indeed the HAL driver. And in this case, for example, if you were to use the TF Lite, you would pass your TF Lite model into the TF Lite parser, and the parser would construct a network for use within Arm NN. And take all the hard work out of it for you, so you don't have to put it together yourself. Once it's imported into the graph builder, it's built up a network, and then it's optimized, which is to say that the optimizer does some validation on the graph, because I guess mistakes can be introduced sometimes. Perhaps there's redundancy, like multiple transpose or reshape operations. So these are all tidied up by our optimizer, and that would be these types of graph optimizations here. But it also modify the network for correctness. For example, perhaps you want to run it on a backend that would prefer to receive it in NCHW format, but you've given a model of NHWC, and so the optimizer would add a permute layer and target the correct backend format. And it also optimizes them for performance too. So we'll see examples of that later. The scheduler is when the optimizer schedules, it assigns the layers in the network to the best available backend to run that layer on. And here you can see our backends interfacing with the compute library in the runtime. So the runtime gets the optimized network, and it executes it on a given backend. Right, so that is what is ARMNN. This is more why. So I've already mentioned ARMNN's easy parsing of different frameworks, which is a great feature. And that gives you access to the compute library to target cores such as Cortex-A as efficiently as possible. And this slide shows these performance improvements and why they're a differentiator for ARMNN. So on the left, you'll see a number of different image recognition models, such as MobileNet, Inception, etc. And the one I want you to look at is actually the MobileNet here for the Cortex-A. You'll see a 4.2 times faster improvement of ARMNN relative to up to 6 different industries' software libraries. And also the mean here, you'll see for both the Cortex-A and Mali GPU, you're looking at 3 times faster, over 3 times faster improvement relative to 6 industry software libraries. So ARMNN shows what's possible for inference, inferring networks optimizations on RMIP. Next is a real world use case, and I'm really happy that I can got permission to show this, because as a developer in ARMNN, it's always lovely to see it actually being used and the end products. So Arcturus networks transform cameras from being passive observers into active detection systems. So their use cases would be for safety and security, surveillance devices, that kind of thing. So motion or intrusion, boundary crossing, we'll say, in a train station, so you're not too close to the tracks, loitering, abandoned package, face verification, that kind of thing. So the Arcturus inference runtimes, they're optimized for edge processing using ARMNN and TensorFlow Lite. The types of models they use include YOLO v3 and Inception v4. And leveraging the Arm v8 Neon engine and utilizing the ARMNN inference network to accelerate performance of a neural network. This allows Arcturus to run detection on Cortex-A cores without the need for specialized ML hardware or a GPU. So for public safety system like this one, edge processing improves the response time and the reliability by eliminating the need to ship pixel data from each camera across the network and up to the cloud. And ARMNN helps Arcturus networks realize that. Okay, so let's look at some of the new features that we have added. PyArmNN. So PyArmNN is a Python extension for Arm NN SDK. Many people use Python through neural network frameworks like PyTorch and TensorFlow. And so I think offering a Python API to ARMNN is a really nice feature. It's essentially a wrapper around the C++ interface. And if you're familiar with our C++ API, it's very similar to use. So as such, it doesn't actually implement any computational kernels, just helper functions, and it's built around the public headers of Arm NN. So all the operations are delegated to the Arm NN library. PyArmNN is integrated into Arm NN's CMake build system, so you can build it that way or separately. I'm not going to get into that here now, but there is a talk after me from Pavel McIntyre, and he has far greater knowledge about PyArmNN, so I suggest that you join that talk if you can. I think it'll be very, very interesting. What I will do is show some code example, because this relates to the flows we were talking about earlier. So you would import your PyArmNN package as you would any other Python package. And what you want to do is create a network from a model file and a parser of your choice. So I'm going to use the ONNX parser and passing in a mobile netv2 ONNX model file. And from that, I'm going to create the network. What I want to do next is optimize that network and run it in the run an inference from it in the runtime. So need to create a few things here. First, we'll create a runtime. To do that, we need to initialize it with some creation options. In this example here, I'm just using default creation options, but we'll see in one of the other features how this can be used and what types of creation options can be added to it. So initialize that, get your runtime object. You also need a list of preferred backends. So this is the order of which we would prefer these backends to be chosen. And then you pass all of that into an optimized function. So you pass your network, your preferred backends, your runtime, get device spec, and this will get the list of backends that are actually available on the device that you're running. And you also pass in some optimizer options. These are not to be confused with the creation options I talked about in the last slide. These are optimizer options specific for the optimizer, and we'll look at those again later as well. So once you have your optimized network, you can load that into your runtime and get a unique network ID. And finally, you want to get your input tensors and output tensors from the input names and binding info from the model. You pass all of that into your in-queue workload function on the runtime. You get your network ID, the input tensors and output tensors, and voila, you run your inference. So, like I said, there's a really good talk after me, and there's also loads of more information on PyArmNN in the README, and we also have examples in that example folder there. It has an object detection sample application in it and a really detailed README on how it all works. Okay, so next feature is the Arm NN backends. So we've already talked about it. This is kind of a summary. A backend is an abstraction connecting layers of a graph to the underlying hardware through a driver or a compute engine. So our existing backends, by default, when you download Arm NN, you get the OpenCL, which represents Mali GPU, and the Neon, which is backend, which is Cortex-A CPU, both of those using Arm Compute Library. We also, by default, include a reference backend. This is purely for testing, just to make sure everything works and you can run it on a device that doesn't have Arm IP. And then, like I said, downloadable is an NPU backend, which would be for accessing the Ethos-N processor. So Arm NN allows adding custom backends through our pluggable backend mechanism. And you can also load custom backends at runtime through the dynamic backend interface. I've sent 2 links here because, again, we have a lot of information in the README. I could probably talk entire talk on both of those features, but those links will help you out if you want more information on them. So currently, globally, if you want to set your preference for backends, this is how you would do it. You give your list of preferred backends. In this example here, I have a custom backend as my number one preference, then a CPU ACC and a GPU ACC. And when Arm NN optimizes the execution of the graph, it does so into subgraphs. So in this example over here, it has been optimized, and layer 1 and layer 2 are supported on my custom backend. So they get put into a subgraph of their own. Layer 3 is not supported on custom backend, so it gets put into a subgraph which is supported on the CPU ACC. It goes to the next backend. And then layer 4 and layer 5, these again are supported on my custom backend, so they get their own subgraph. And that is the order that is used all the way right through your model. Our new feature is for power users of ARMNN, and what it does is you can specify your preference per layer. So if you set this backend hint, it's treated as the first most preferred backend to select during the backend selection phase of the optimizer. If it doesn't find support for the layer, we use the normal fallback that you saw in the previous slide. And this is how you would do it. You add the following method to the iConnectable layer interface. So when I was talking about using our API, the direct API, to make layers and connect them together, you'd use this object on iConnectable layer. And we've added this backend selection hint. So you can tell a specific layer as you're creating your model, I want this one to run on this specific backend ID. Now there is a caveat, so if the user wants to load a model using the parsers, there's no handles to the layers while the input network is being built, so you cannot explicitly set that backend hint if using the parser. But we do provide an iNetwork accept layer visitor interface, and with a little bit of C++ knowledge, you can provide a custom visitor class which would identify layers in the graph in order to set the backend hint based on your custom rules. Okay, this is the second backend feature. So in the 2002 release, we introduced a new API, backend options, for passing parameters directly to the backends. And the backend options are added during the initialization of the runtime. So if you recall, when the PyArmNN example, we had a creation options that we added when we initialized the runtime. Well, the backend options are a member of those creation options. You'll see that now in a minute. I'm going to demonstrate using this new API with an existing feature we have called a GPU ACC tuner that previously had its own API. So the tuner is a module of Arm Compute Library, and it can improve the performance of the OpenCL kernels by tuning the local workgroup size. So you can give it a file and it will learn the correct values to write to the file, so you can have a trade-off between the time taken to tune and the kernel execution time achieved. So here's an example. I'm using C++ code here, but you can see it's quite similar flow to the Python code. So here I'm creating my creation options, but before I initialize my runtime, I'm accessing the backend options on it, and I'm placing back into that my custom parameters for the GPU ACC backend. So here I am referencing GPU ACC backend, and these are my custom parameters. So in this example, I'm picking a tuning level of 2, and I'm also passing in my my file where I want to write that data to, the tuning information. And then it's just a matter of initializing your runtime. You pass your creation options in once that's been set. I have here as a note, if you want to actually then execute that tuning data, you would just start up with the tuning file specified and not the tuning level. Okay, So the next feature is the data type support. So in 2005, we added some new data types and we renamed some data types. So the existing data types we had were quantized ASIM8, which has been renamed to QASIM U8, Q asymmetric, unsigned, 8-bit, and quantized SIM16, which would be QSIM S16. And then we added these two new data types, QSIM S8, QASIM S8, and then the bfloat16. So let's have a look at those. The QASIM S8 and the QSIM S8, in the 2002 release, we updated TF Lite to 1.15, and the new TensorFlow Lite 8-bit quantization specification uses int8 instead of uint8 to hold the payload. So to support this, we added these two new data types, quantized asymmetric signed 8-bit integer type and the quantized symmetric signed 8-bit integer type. Asymmetric means the 0 point can be anywhere within the signed int8 range, so minus 128 to 127, and activations would be asymmetric. And symmetric then would mean the 0 point is equal to 0 and weights are forced to have their 0 point equal to 0. So we provided support for this for TensorFlow Lite, and we also updated the Android NN driver to support the corresponding data types in those. And we also added these are two other programs that Arm NN comes with. The serializer, a tool for serializing and deserializing Arm NN network to a stream, and the quantizer, a tool for converting a 32-bit float network into a quantized asymmetric 8-bit or symmetric 16-bit network. So we added the support for those as well to that. Data type support. So the bfloat16, in 2005, we added bfloat16 data type support. And what that is BF16 provides an easy way to accelerate FP32 networks with a smaller loss in accuracy compared to FP16. So the benefits would include reduction of memory footprint and computation speed up compared to float FP32, but more accurate than FP16. So the existing FP16 turbo mode, what it does is it adds a conversion layer before the inputs and or after the inputs and before the outputs, so that the inputs and outputs are still FP32. And then any layers that can be supported within would be FP16. So our second turbo mode does the same, and this is how you engage that. So you create your optimizer options. Again, this is C++, but it looks quite familiar to the flow we saw in the Python API. And you call the member on it here, reduce FP32 to BF16 and set that to true. And then it's just a case of you passing your optimizer options into the optimize function as per usual. And our optimizer takes care of the rest. Okay, I'm getting very close to the end, I see, for time. I will do this one quickly. So Android NN operators, we're always adding them. These are the ones that we added in HAL 1.0 and 1.1. They're also available to HALs 1.2 and 1.3. And here in orange, you can see all of the new operators that we have added since the 1911 release. So there are quite a few there. We have added not just to the HAL 1.2, but we have also added to the HAL 1.3. We've added ELU and the fantastically named hard swish, which are activations with their own benefits, and then some helper operators like fill, which will fill a tensor with a scalar value, and a rank, which will report it as a number of dimensions of a tensor, and then QLSTM, which is quantized long short-term memory used for speech recognition. So while we've added a lot, there are always more to add. So I'd like to finish then with these slides, which would be if you would like to contribute or add an operator or indeed any other feature to Arm NN, this is how you would do it. So Arm NN is currently open source, it's MIT license. It uses continuously integrated development model. We undertook that when we were accepted as part of the official artificial intelligence initiative of Linaro. And every commit to master is publicly available on review.ml.platform.org. We also mirror those on GitHub, the master, and we make releases to GitHub, but the action is on ML platform Gerrit. So you can set up your GitHub account, set up your name, your email address, and once you patch for your push for a patch for code, you would sign off, and the patch will appear on ML platform Gerrit here, and more than likely somebody from Arm NN will review, and once that gets merged, that's available for everyone to take advantage of on the master. So I think I may have gone quite close to time, or if not over. So I can leave it there and see if there are any questions. Hang on now.
There's one question, Kevin, that I've moved over to from Zoom over to Slack.
Yes. So any plans for Arm NN integration with NVIDIA hardware software? I'm not in a position to talk about that. So unfortunately, I can't answer it. I wish I could, but I am not aware of it or privy to it.
Okay, understood.